So let's check the linearity of this given differential equation. We have the quantity x squared plus y squared times dx is equal to, minus 2xy dy equal to 0. We separated this in the understanding or identifying its linearity because here it's not very clear which would be our dependent and independent variable. In our first video for this chapter, we're able to say that it could either be x or y being our dependent and y and x independent or vice versa, depending on how you will attack this given problem. But we're talking about linearity for ordinary differential equation. It should satisfy this general form where a sub n times, if it's I'm just going to write it first, x, we have the nth derivative of order derivative of y with respect to x plus another constant times x, and then you have here the nth minus 1 derivative order derivative of y with respect to x dot plus a sub 1, and you will have here another x, the first order derivative of y with respect to x plus a sub 0 times x times y is equal to a certain g of x here. So this is for the linearity of ordinary differential equation. What you can see here is this. If you're taking about the derivative of y with respect to x, and of course it will follow here depending on the order, you will have here your variable y, and you can see that your independent variable is here on its first order. Okay, I mean not first order, I mean its exponent is 1. Okay, so exponent is 1, and you will have here g of x here. Okay, those will be the ideas that we may use for the rest of the explanations as we talk about the linearity of this. So let's attack this first. This given equation, x squared plus y squared times dx minus 2xy dy equal to 0. Let's take whether this is a linear in the variable y. So in y, that's what we're talking about. We would like to use y as our dependent variable. Hence, we will be dividing all of these terms by dx. Of course, 0 divided by dx is 0 itself. So we will have here x squared plus y squared, that's cancelled out, minus 2xy. You have here dy over dx, or the first order derivative of y with respect to x, equal to 0. Let's try to transform this given expression into our, what they call this one, in this form here. If we could achieve that this differential equation is linear in the variable y. But if we can't do that, then we can say that this is non-linear in the variable of y. Since we would like to have variables x here, because this is the point here for our independent variables x, so you would like to see x's here, and there. We don't want to see y in this left hand side. So what we could do is to divide both sides or all sides by, let's say, a certain y, because we would like this one here to be removed, as we have, you can see in this form here, we'll be dividing y first on all the terms here. So you will have x squared over y. Your second term is just y because that's y squared over y, minus 2x, y will be removed. The first order derivative of y with respect to x is equal to 0. So we have probably achieved this form now. And then since y could satisfy this form here, so we could rearrange it as 2x, the first order derivative of y with respect to x, minus 2x if you would like to, and you will have here a certain plus y. Okay, and since this will not fit any of the terms in our linearity for ordinary differential equation, you can move it on the other side, minus x squared over y. If you would like to multiply all terms by -1, you could also have this 2x times the first order derivative of y with respect to x. Sorry, this will become minus now. Okay, minus y, and this will become positive x squared over y. So this form here follows this form here for linearity. Okay, so we have your a sub 1 is 2, you will have your x probably here. Yeah, 2x. That's it. And then the first order derivative of y over in terms of x. And your a sub 0 is -1. And if I'm correct, x is 1, so you have y. But this is still non-linear because take note of the form for linearity. It should be equal to a certain function of x. Yes, there's x here, but there exists y. This violates the idea of linearity because it should be that after you're forming here a certain form that follows the linearity for ordinary differential equation, your left or your right hand side rather should only contain a function with variable x, but there exists y here. This is why this form is non-linear in y. Okay, so this is now sure to be non-linear for y. Now, how about it being in x? Let's try if this is linear in x, because it could be the other way around where we pick our x to be our dependent variable and y will be our independent variable. Let me rewrite here x squared plus y squared. I believe this was 2x dx minus 2xy, and dy is equal to 0. Instead of dividing both sides by, or all terms by dx, let's divide all terms by dy. So you will have here x squared plus y squared, and you have your dx over dy. In short, we are taking now the derivative or the first order derivative of x in terms of with respect to y. The other side will be 2x y, and then dy will be removed equal to 0. So just like earlier, we would like to show, so that would mean this should be y, this should be x here. The problem now here is looking into this form, just for this form alone, the first order derivative of x in terms of y, we should follow this idea here. But this should only be with a constant, the variable, or specifically the independent variable, because that was s earlier, and this notation here. But what you can see, yes, you can say that your constant is 1. It follows that. This is your first order derivative of x in terms of y. But your variable here is not y alone, because it should be y alone here. Okay? It should only be y so that it could satisfy the idea of linearity. But you will have x squared and y squared, which could not be broken, because even if you're going to break that, you could still see a variable of y in terms of second degree, and it doesn't follow here because all of our x's are of exponent 1, exponent 1, exponent 1, exponent 1. Okay, this in turn also making our equation nonlinear in x. In short, our given expression earlier is both nonlinear in y and nonlinear in x. So this is for our video explaining the linearity of our given differential equation, where we could take both sides for our x and y. We might have another example for this soon, but for this time, thank you very much for watching.